Yeah. Welcome students to this second lecture on laws of motion. Okay. So in this lecture, uh, we'll be discussing about inertia and Newton's first law of motion. And I hope that the earlier video you have seen it maybe once, at least twice, thrice. Okay. So that you understand the idea behind those experiments conducted by Galileo. So in the last video, we had discussed Aristotle fallacy, then how Galileo showed that his fallacy was basically wrong. Okay. This video will try to discuss what is basically inertia. Okay, so inertia, as the word goes, so this word inertia, and before I go to this inertia, okay, uh, we'll come to the next important thing, that is who was basically Newton or what was his background. Okay, so if you see, Sir Isaac Newton, that's what we call him. He was what do you call it as? He was a natural philosopher. That's what they say, right? And you can see the age around. That is, he was born during that time, 1642 to 1726, right? And whatever theories which we work on today, okay, they are basically based on this. At least the mechanics part. Of course, it doesn't. Some of the theories don't work at microscopic level, but surely at macroscopic level, most of his theories work till today. You can see the theories which were developed some 300 years back. Okay, so uh, Newton's thing. Okay, first of all, Newton, by seeing the experiments conducted by Galileo, okay, he came to a conclusion that surely it's not required that there should be a there is a force necessary to keep an object in motion. But then practically there are certain things which come into play. Like for example, frictional force, other things. In order to overcome, you require force. Otherwise, you don't actually require force for an object to be in basically motion. Okay, so now we slowly come back to this word, which is basically inertia. Okay, so inertia is a word which has to be understood as something like that. That it's the nature of an object to be in a state of rest or in a state of uniform motion. Okay, now it's the intrinsic nature. The meaning of the word intrinsic is it's the nature of the object itself. Like it has its own nature, that a object, like for example, if a object is at rest, like if you keep a book at rest, okay, if you come today, tomorrow, day after tomorrow, after 10 days also, unless and until nobody has moved it, okay, the object is going to be in a state of rest itself, right? So if an object is in motion, okay, this object will basically continue to be in motion unless and until something doesn't stop it. A simple example, you can say that, for example, if I throw a ball at you, okay, and you catch the ball, while you were catching the ball, you had applied some force, okay, and that's why the ball basically stopped, because you have applied some force. Otherwise, the ball would have continued. But again, it naturally comes down because of this air resistance is there, then friction is there, which are natural there. But if there wouldn't have been any forces, then the object would basically come to would never have stopped. Okay, so these are the few examples which we'll just try to see. Okay, so first we'll try to see example where the object, okay, so where the object is in motion, okay, is at initially at rest, we'll see, then we'll see the object situation in motion. Okay, now inertia and mass, they are related to each other in the sense mass is the measure of inertia. If I want to measure inertia of an object, it is the mass which will tell us how much inertia. So basically inertia can be put in one more way, that it's the resistance of the object to change its state of motion or of rest. Like for example, if the heavier object is there, like if I tell you to take a book and keep it over other end, okay, very easily you will take the book and just keep it over the other end. Okay, but the same thing, if I tell you take this heavy rock and keep it at some other distance, then that becomes very difficult. That heavy rock will have more mass, so it will try to resist more in the change of state. Okay, and that's why the word, or you get a normal question in examination, what is the measure of inertia, and the answer for that is mass is basically the measure of which one? Inertia. Okay, so once again, the two important things about inertia is it's an intrinsic nature. That is the, and any object, it will have its intrinsic nature, that it will basically be in a state of rest or in a state of uniform motion. Okay, then the next important thing about this is that how do I measure inertia? Okay, so inertia is measured in terms of mass of an object. See, if if I tell you to catch a simple plastic ball, okay, that you can very easily catch. If I throw a plastic ball at you, that you can easily catch it. Okay, but if I throw a shot put at you with the same velocity, okay, you won't be able to catch it because its mass is more. So to change its state of motion to rest, that becomes a bit difficult. Okay, so inertia has what we call it as, we have three types of inertia which we will discuss. First is inertia at rest, right? Then you have what is called as inertia of motion. Then next we have what is called as inertia of direction. Okay, motion and direction we can see together also sometimes. Okay, so inertia of rest is that object continues to be in a state of rest unless and until something doesn't act on it. Inertia of motion is the object will continue to be in a state of motion. Okay, so these are the examples which we will try to understand here. Okay, so say for example in our this, in a simple example here. Okay, so what we'll do here, what is done here is, as you can see over here that, okay, uh, what we have done here is like, you have this tube here, okay, or a flask is over here, and then you have a ring, and then you have an object which is placed over this. Okay, now what do you think will happen if I just hit this ring? Okay, you will see that the moment you just remove the what do you call it as, if you just remove it, okay, the ring is, if the ring is suddenly removed, the object instantly falls down. Why did the object not go with the ring? The reason for that is that the object was at rest. There was no proper connection between the there was no, like for example, the ring, the object over the ring was not maybe glued or maybe fixed with the ring. Okay, it was in the state of rest. Okay, when the ring was moved, it maintained its state of rest because as such no direct force was acting on it, and because of that the object, as you can see over here, that when the ring was removed, the object directly fell. Okay, because it was in a state of rest, the object which was over the ring, right? Now the same example over here. Okay, if you can see, a bigger ring is taken, right? And again if it is suddenly removed, okay, just see, if the ring is suddenly removed, it maintains its state of rest and it again falls in the flask. Okay, you can try this example where you take a beaker, okay, keep a coin over a paper, okay, and then again you can explain the same thing on the basis of inertia, that the coin was in a state of inertia and suddenly when you removed the paper, it was still maintaining its state. It was still maintaining its state of which one? Inertia. And because it was maintaining its state of inertia, it did not move with the paper. Okay, and then the coin directly falls down over there, right? Now same thing here. Here we'll see that more, like for example, again the situation that a paper is being dragged out of this beaker. Okay, and you can see that as the paper is being dragged out, okay, what happens, the beaker was again in the same state, that it did not come with the paper, it is still maintaining its state of which one? Rest, even though you are dragging the paper below it. Okay, so these are the examples where inertia comes into play. And which type of inertia are we talking about? Is it rest or motion? The object here, if you see the object over here, okay, the object here was in a state of rest and I removed it, it fell down, it maintained its state of rest. Here also the object is at rest, I removed the sphere over that, it again maintained. In this example also what we see, the moment I remove the paper, it maintains its state, the point there, it maintains its state of what you call it as rest, right? And here also, even though I'm trying to remove this paper over here, okay, it is still trying to maintain the state of rest. The beaker tries to maintain the state of rest. It has heavier mass. Heavier mass, more difficult it will be to remove or make it move. Okay, and it is in a state of which one? Rest, right? So these are few examples which you can actually try also. Okay, where you can see that when an object is just moved, okay, it maintains its state of rest. These are the examples where it's the inertia of rest. So as I told you, there are three types of inertia which we will discuss. The first one which we discussed from these examples are the inertia of which one? Rest. That object tends to be in a state of which one? Rest, right? Now let us say for example, we'll take another example where a person is going in a bus, okay, and say he's just hanging over you the bus, as you can see, okay. Now the first situation is when the bus, say for example, suddenly moves, okay. Now if you would have observed here carefully, say the initially the bus is at rest, okay, and suddenly the bus starts moving in forward direction, you can see that the person feels a jerk in backward direction. What must be the reason and how do it's another example of which one? Inertia. So here what is happening here is that the lower part of the person, okay, so the lower part of the person, it is at rest and it is slightly connected to the surface of the bus, okay. So it starts moving, the complete body was initially at rest, the upper part of the body, it remains in the state of rest, whereas the lower part starts moving, and that's why you feel that this is actually in rest, okay. So it's not that it is jerking forward, actually the lower part is moving in forward direction, upper part is still at rest, and that's why the person feels a jerk in which direction? A backward direction. So as you can see here, okay, so this is how it happens basically, okay, that the moment, okay, the bus starts, the object, the person, he feels a jerk in which direction? Backward direction. And the same thing, the reasoning here is that the upper part of the body was in a state of rest, okay. And if you see the diagram over here, okay, the lower part here, okay, it is in contact, okay, yeah. So the lower part actually is moving, upper part remains there only, so it looks as if the person is going in which direction? Backward direction, okay. So this is another example where you have the object which is at rest, okay. So this thing can again be explained in terms of which one? Inertia, okay. So inertia is a state again that object is continuing to be in a state of rest or in a state of motion. Now let's see further, okay. So for example, a vehicle is taking a turn, okay. So you must have seen that if the vehicle is taking a right turn, the person is moved towards the left, he maintains his state of what you call it as inertia of direction, okay. And as you can see over here, that the moment he takes a turn, you can see the person is shifted towards which direction? Left direction, okay. And again, like for example, this type of inertia is basically called as which one? The inertia of direction. That if you see here, that the person, when he was taking this turn, okay, so if you take so if you are going in a vehicle, you won't be turned in the same direction as the direction of which one? Yeah. So just see, if you are going in a vehicle and you are taking a right turn, you will be automatically, you will have a push towards which side? Left side, because you are maintaining the inertia of which one? Direction. And again the lower part is moving right side, your upper part is in the directional motion which is in the straight line, and that's why you feel as if you are being tilted in the opposite direction. So this is an example of which one, inertia of which one direction, right? And say for example a object is moving and suddenly is brought to rest. Okay, so when the object is in motion, okay, and this object is now suddenly brought to basically rest, right? So you will see that if a object which is in motion, say for example, is brought to suddenly rest position, again the same thing will happen over here. Your complete object, your complete body was earlier in motion. It had the same motion as the motion of which one, the vehicle over there. Okay, but the moment the bus stopped, the lower part of the body, that lower part of the body which is like for example the feet which is attached to the bus, that initially gets stopped. It has almost the same motion with that of the bus, but the upper part is still in motion, so it tries to maintain its motion and is basically trying to go in which direction, forward direction. Okay, so here we have what is called as a simple example of what is inertia of basically motion. Okay, so in this diagram what happens, the bus is in motion. Okay, so the upper part of the body, the complete body is in motion, but the moment the bus stops, the lower part is at rest, whereas the upper part of the body, it basically continues to be in the same motion. Okay, and that's why whenever a bus stops, okay, whenever the bus stops, you have the situation of what is called as, you feel a jerk in forward direction. Okay, like you must have seen, especially as a student, you must have seen that. Say for example you are sitting on your friend's bike and your friend suddenly starts the bike. Okay, where do you feel the jerk, forward or backward? You will feel the jerk backwards, because your upper part of the body is at rest but the lower part of the body is pushed with the vehicle. Okay, so same thing is, if you are going in a vehicle and you are sitting behind and suddenly brakes are applied, you tend to move in which direction, forward direction, because you are maintaining the direction of the motion as seen in this example. Okay, so these are very important examples, okay, which basically tell us how this friction it comes into play, or there is how this inertia comes into play. So as you can see, the this particular example where the upper part of the body still is in motion but the lower part is rest, so the person feels a jerk in which direction, forward direction. Okay, so here we discussed what is called as two types of examples. Okay, initially it was an example where this was the example where the person was at rest and suddenly the bus started. Okay, and this is the example of an object which was inertia of rest. Okay, and because of this, earlier the person was at rest and he felt the motion in which direction, backward direction, right? And in the second example over here, we have the example which is inertia of motion, where because of this, because the moment the bus suddenly stops, okay, like here, okay, say the bus is in motion, it suddenly stops, you get the jerk. This is an example of where the object was already in motion and it suddenly comes to which one, rest. Okay, so you have these two types of inertias here. One is what is called as inertia of rest, inertia of motion, and this example where the person, you know, like when you take a turn, okay, this is example of what is inertia of direction, right? Because of the inertia of direction, if a person is studying towards left, he'll feel a deflection towards the right side. Okay, so you have one more example here. Again, I'll come back to the same statement that we have again three types of inertia. One is inertia of rest, inertia of motion, inertia of direction. See, in space and all, if you see example of space, okay, like if an object is moving in space, you will see, like even for example, our in our solar system, Earth is continuously moving around Sun. Okay, the reason here is that it also has an inertia of we call it as inertia of rotational motion. There is one more inertia which we'll discuss later on. Okay, That is the inertia of rotation motion. So if, as Newton said, very important thing, that if there wouldn't have been any frictional forces, if there wouldn't have any air resistance forces, okay, then the object would have basically continued to be in motion. So that is the reason why very long distances in space, okay, we are able to, like for example, move through space. Like there have been spacecraft sent to Mars, okay, to Moon. The idea here is that once you give the direction to them with certain velocity, they will just maintain the velocity. You don't require fuel. You don't require like 60 km per liter, those type of fuel, okay, because once in space, okay, so once you have put the particular spacecraft or rocket in space, okay, and you have given it a particular motion, it continues to be in that state. Okay, let us say this particular example is like, once the reason for that is, as there is no friction over there, okay, so these objects in space, especially the best example is like inertia is the inertia in space. Okay, so initially what you do is you just give the initial acceleration to the rocket. Okay, and in space this rocket will just go on moving without any fuel required. Okay, so it's because of, again, you can explain this term in terms of which one, inertia. So whenever you see the whenever the rocket is being blasted, that time it accelerates, okay, and achieves a certain velocity. Like here, initially the rocket gets blasted, means the reason is it will try to attain some velocity. Okay, once it has attained some velocity, you just have to stop the blasting process, okay, and then it will just continue to move in its own motion. So here, which type of inertia do we discuss, or what is the type of inertia? Inertia of which one? Motion. That once you keep, once an object is in space, it is being sent in space, unless and until something doesn't stop it. Okay, it's just going to go freely in space. And what is the reason for that? What must be the reason that on Earth, if I hit a football on the ground, the football basically just stops after moving a certain distance, but this spacecraft doesn't stop. Okay, so the reason for that is, again, you can explain in terms of which one, motion in space. When an object is moving in space, first of all there is no atmosphere there, so there won't be any air resistance, there is no friction over there, and therefore because there is no opposing force, okay, that's why what happens is the object continues to be in the state of motion. Now same thing, like for example, why is it told that you should have this you should have this belts over there? The reason is, say for example, any person inside the car, when the car is in motion, he is also in the same state of motion. Okay, the moment if a car accident undergoes an accident, okay, what happens? You can see in the diagram, okay, that the person is still in motion and he continues to be in a state. So here, say for example, if it is binded, there is a chance that you can just collide with the your screen over there, that is uh, to any object. Okay, so you'll be just thrown away. That is the reason why you should why seat belts are worn. Okay, because our body, even though in the car you feel that you are actually at rest, when the car is moving, you feel that you are in rest, but it has a motion same as that of the car. And the moment anything, if anything stops, or if any object interferes, or just like this a block comes, then the car stops, but you are still in a state of motion. Okay, and that's why especially in bike accidents and all, the, say for example, a bike comes across such an obstacle, okay, the person is just thrown off. It's an example of which one, inertia of motion. Okay, so uh, with these examples, now we can come into what is called as, we can just try to understand this Newton's first law. Okay, so what Newton says, okay, that every object will continue to be in a state of rest or in a state of uniform motion unless and until acted upon by an external agency. Okay, and this word here, okay, so same statement as inertia. What is inertia? What is slight difference between inertia and Newton's first law? Inertia says that it's a nature that the object will be in a state of rest or in a state of uniform motion. But Newton's first law slightly it says that it will continue to be in a state of rest or in a state of uniform motion till what time? Unless or until acted upon by an external agency. So Newton used the word external agency, and then slowly we have the origin of force. Force is nothing but that external agency which causes the state or causes the change in state basically. So if you want to make an object from rest to motion, you require a force. If you want to make an object from motion to rest, bring back an object from motion to rest, then also you require which one? Force. So Newton's just this external agency which we are discussing here is basically today we understand it as which one? Force. Okay. So this is a statement of Newton's first law that every object continues to be in a state of rest or in a state of uniform motion unless and until acted upon by an external agency. So there is one more way in which you can understand this, that the object, I will tell when I say this word over here, okay, I'll just go back to this important point over here, okay, and I'll just okay, we'll just underline this word here. The word I am trying to underline here is uniform motion. Okay, now I didn't say that any motion here. Okay, as a student, you have to understand this word uniform motion basically means a motion where neither there is an increase in velocity, neither there is a decrease in velocity. Then what must be the acceleration there? So, if an object there is having a constant velocity, neither there is an increase in velocity nor there is a decrease in velocity. Okay, then such a motion is known as a uniform motion. Okay, that so there are three things. That means the object's direction also should not change. Okay, neither its velocity should increase, neither its velocity should decrease, nor its direction should change. Like in the second topic, like is in motion in a plane, we have studied that velocity is a vector quantity. So I am saying that object is said to be in uniform motion when its velocity remains constant. Okay. So when I say velocity remains constant, it basically means that neither it's having any acceleration, nor it is having any retardation, which is the decrease in velocity, nor is its direction changing. Right. So that is what Newton says. So put it in another way, that if there is if the net force, so this is how you have to, one more thing you have to understand here is that if the net external force acting on an object is zero, then its acceleration is zero. Net force, okay, it's not that if an object is at rest there are no forces acting on it. Okay, there are situations where object is at rest but still a number of forces are acting on it, right? So that's what we'll just try to understand. That another way, of course, before we try to understand it, there is another way of understanding this Newton's first law, so very nicely given in textbooks. Okay, that the object will have zero acceleration. Okay, because you are going to solve a number of problems based on this concept also, that object will have zero acceleration if the net external force on that particular object is zero. So zero acceleration doesn't mean its velocity is zero. It can have a constant velocity, just like an object going in space. Okay, if the object is going in space with a constant velocity, okay, like the example which we took over here. Okay, so here if the object is going in space with constant velocity, that doesn't mean that uh, what you call it as the net force on the object is basically what the net force on the object has to be zero. When the object is accelerating, there was some net force. Okay, but once the object is going with constant velocity, then we say that the net force is which one? Zero. So I want you to understand this word which I have underlined over there. Uniform motion means what will you say about the three conditions for uniform motion? The first point here is that it shouldn't have any acceleration. The second point is there shouldn't be any retardation. And the third point is that there shouldn't be any change in direction. So every object will continue to be in uniform motion unless and until acted upon by an external agency, or if the net external agency acting on an object is zero, then there would be any acceleration on it. Okay, so this is how we basically try to understand what is called as Newton's first law. So as I was telling that net force should be zero. Okay, just we'll take an example of this book which is kept on the table. Okay, so when a book is kept on a table, there is a force of gravity which is pushing it downwards, and there is a reaction which is pushing it upwards, and both are equal. Okay, so as both are equal, what happens is there is a net force is zero. Okay, and because the net force is zero, the object is basically at rest. Okay, so here we have that it's not that no forces are acting. So as a student of physics, you should understand that it's not that forces are not acting, but if the net force is zero, like always on any object on the on earth, there will be surely a force acting, and that force will be, say, like in this example, the force is acting in which direction? Downward direction. Okay, this is the gravitational force, right? And but because it is kept on the table is giving a reaction upwards. Okay, and that's why the net force on this table, or sorry, on this book is basically which one? Zero. So let us say, for example, in day to day, that there is one more way in which the net force on the object can be at rest. Like for example, I am trying to pull a table and the table is not being pulled. Okay, I'm trying to pull a table, but say a small child is trying to pull a table. Okay, so table is heavier. Then why is it that the table is still at rest? The reason may be something like this, that on a table, how many forces may be acting? So just see. The first force will be the weight acting downwards given by mg. The second force will be the normal reaction, which is the reaction coming from the table over there. Now the boy is applying a force Fa, but here this applied force is not equal, not sufficient to cross this frictional force. So this applied force here and the frictional force here, both are maybe same. Okay, and that's why the net force on this object is zero. How do I calculate net force here? I will see whether net horizontal, this is the horizontal force. Okay, these are the two vertical forces. So weight is down. Okay, just concentrate on the word which I am using here. Vertical force, forces acting along, say, y-axis. Okay, so the vertical force, net vertical force is zero. The weight is acting downwards. Normal reaction is upwards. The net horizontal force is zero. Applied force is this side. The frictional force is towards the other side. Okay, so because there is the net vertical force is zero, the net horizontal force is zero, the object is at rest. But as the statement goes again, why the object is at rest? Because it's not that force is not acting on them, but the net force, okay, the net external force acting on the object is zero, hence its acceleration is basically zero, or the object is basically at rest. Okay, let us take an example of practical example. Say a car is going with a constant velocity. Okay, so if a car is going at constant velocity, surely the car has some weight. Please remember the word I'm using, that word which is constant velocity. Okay, so if the car is going with constant velocity, then this car will have some mass. Okay, so all of you, I think you are clear with this formula here, that I have written weight as not mass. Okay, so weight is mass into acceleration due to gravity. On earth the gravity is 9.8, so weight is m into g. So coming back to this example over here, so this car will have some mass m into g, that will be the weight. The weight will be acting in which direction? Downward direction. Okay, the surface will give a upward force to it. Okay, so there will be a upward force which will be, we call it as which a normal reaction, the reaction which we get from the ground. Okay, so that will be equal to the weight, right? So that is the force which is coming upwards. But you can see that the car, even though it is going with velocity, the engines are on. Why should the engines be on? Okay, so the reason here is that,
look at a vehicle moving at a
okay, so say for example in this here there is an applied force on which the car has. Okay, this applied force on the car is because of the engine which are trying to push the car in forward direction, but there is a frictional force acting in which direction? Backward direction. If I assume that the car is going with a constant velocity, okay, so here if I assume that the car is going with which velocity? Constant velocity, then what should happen? The applied force by the engine should be equal to the frictional force. Okay, so whatever is the applied force, so applied force is not more than the frictional force. Okay, so the applied force, if it is almost equal to the frictional force, so you have balance of horizontal forces. The weight acting downwards will be equal to the weight acting upwards. You have the equal, or for example the vertical forces are again cancelling each other, horizontal forces are cancelling each other, and in such a situation, now what happens is the car basically starts moving with which velocity? Constant velocity. Okay, so here a bit more compared to what you had studied in 9th or 10th, you should understand that the object can maintain a constant velocity. Say you are going in a car with a constant velocity, it doesn't mean that there is no force applied. Practically, now you should be very practical because now you are in PUC first year. Okay, so if a car is going with constant velocity, say you are driving a car at 60 km per hour, then what is happening at that situation is you are only applying the force which is overcoming the frictional force of the between the tires and the surface, right? If you don't apply this force, then there will be always a frictional force and the vehicle is just going to stop. The frictional force acts opposite to the direction of motion, the vehicle will stop. Okay, because you are applying a force, and if your applied force is almost equal to the frictional force, that time what happens? You can basically maintain the velocity. Just think over it. If your applied force is slightly less than the frictional force, if your applied force is slightly more than the frictional force, what will happen? If applied force is slightly more, the vehicle will increase the velocity. If your applied force is slightly less than the frictional force, your vehicle will be moving, but its velocity will be decreasing. Okay, so this is how you basically understand that even if the object is in motion, there are a number of forces acting on it. Okay, and these forces, which we try to understand here, that even though the net x, that's why I'm trying to make you understand this another word here, net word. Okay, which I'll just underline here. Okay, so the word which I'm trying to understand is underline here is this net external force. Okay, so this net external force, when I say, is the sum total of vertical forces should be zero, horizontal forces should be zero. That means left hand side force should be equal to right hand side force, upward force should be equal to which one? Downward force. Then the object doesn't have acceleration. But again, don't get confused. Even if acceleration is not there, like in our example, see the word which is coming over here, it's constant velocity. Okay, so if the acceleration is not there, doesn't mean that the object is not having any motion. Okay, the object has net acceleration zero, but it's moving with which velocity? Constant velocity. Okay, so to summarize this Newton's first law, so if the forces are balanced, then the acceleration is zero. Okay, so if an object is in motion, okay, if the object is at rest and the net external force is zero, the object will stay at rest. If the object is in uniform motion, okay, now uniform motion again is that where acceleration is zero. Okay, so object will be in uniform motion. If the net forces are balanced, it will continue to be in the state of which one? Uniform motion. So basically, you can see in this green line words here that uniform motion means two things. Their speed should be same. That means they should be say 60 kilometers. It should maintain 60 kilometer also, and direction also is same. I'll tell you an important point to just think over that the moment you are trying to change the direction of the car, that time also you are accelerating. And maybe you must have come across the word centripetal acceleration. Okay. So we are not talking about a change in direction. So we are talking about uniform motion where velocity is constant. Okay. So if there are no forces acting, object at rest will stay at rest, object in motion will stay at motion. Okay. So these are the things which we have discussed. Okay, to understand the basics of physics. Okay, just you can go through this video once again. If it's better that you go through this video once again, go through the earlier video once again, and the things will be very clear to you that what exactly is Newton's first law. Okay, and how it can be applied in day-to-day life. You can see the situations which happen in day-to-day life. Okay, so with this I'll conclude today's lecture here. In the next lecture we'll try to understand Newton's second law and then third law. Okay, so just go through the lecture. Yeah. Thank you all of you.